Good morning, everyone, and welcome to the ITC 2024 Diamond Sponsor Presentation. Please welcome to the stage our next speaker, Vishal Agarwal. He's a Senior Director at NVIDIA.
Hi, everyone. The topic for my talk today is pursuit of quality for large, complex AI systems. Quality is the end result of test. Test indicates cost that people want to optimize. Quality conveys benefits that people want to invest more into. At NVIDIA, we find it more meaningful to think in terms of quality first, and then working backwards to figure out the most efficient solution that will get us there. For a few years now, we have been working very closely with the Siemens team on developing our new scan solution. I will share some of the important thought processes that went into this development, the challenges that needed to be solved, and some results from our silicon bring-up. This slide may look familiar to some of you. It is copied from the launch presentation of NVIDIA Blackwell by our CEO, Mr. Jensen Huang. This is the most complex chip ever made at NVIDIA, and the most important product for AI in the world today. Blackwell is two reticle-sized chiplets connected together by a very high-speed interface. It is surrounded by 8 HBM dilets on the substrate. Blackwell-based systems deliver 4x higher AI training performance, 30x better AI inference performance, and provide 25x better power efficiency versus Hopper platform, the current market leader in AI today. Alongside these truly impressive capabilities of Blackwell, RAS, reliability, availability, and serviceability, and IST, in-system test, they are also called out as a product launch feature. The reason is very clear. There are 200 billion transistors on a single chip. 100,000 of these chips work together for weeks at a time, solving important AI problems. The quality requirement for this kind of system has to be extremely high. Let me start by sharing some important details about our existing scan solution. NVIDIA maps mechanism for accessing test over a high-speed interface like PCIe. We attach a PC to the side of an ATE and use it to drive a very large amounts of test payload at a very high throughput of PCIe. This allows us to bypass the traditional test time and memory constraints of a standard ATE setup. The complete solution, consisting of system architecture, hardware, and software, was developed by DFX team at NVIDIA in close collaboration with several other teams. Our previous scan solution was also largely an in-house development. This time, we decided to redesign it using the best solutions available in the market today. This was a major change in our strategy from the past and carried considerable risk. There were 4 pillars to this solution. The choice of architecture is arguably the most important decision in any project. We designed our new solution using Tessent SSN architecture. At the time, SSN was not publicly announced. However, the benefits of a streaming packet-based scan architecture, they were very clear to us even then. We also rewrote our scan insertion flow using Tessent Scan Pro. Our final solution allowed us to get the full design performance from maps and supported all of our important use cases. I want to thank the Siemens engineering team again from this stage for their very close collaboration through this project. As most people here would agree, verification can make or break a project. Blackwell was a very, very challenging design to verify. It had 500 million scan flops, 2,000 SSH. Our biggest block sizes could be up to 10 million flops. At this scale, the runtime for standard things is days and weeks. And then you have to think about debugging these very long-running jobs. To meet this challenge, we have taken the concept of left shift to its limits. Almost the entirety of verification risk is covered in RTL. All gate level steps are executed using a correct by construction workflow. and therefore we have very few debug iterations at these long-running steps. Second, we have worked very hard on building the core competencies in ASIC verification methods, things like UVM, emulation, and FPGA, and we find them very, very effective in solving some very complex DFT verification problems as well. The third piece of the puzzle is automations. By deep automations, I'm referring to our centralized automation stack. Every single DFX operation, from RTL integration to scan insertion, from DRC to ATPG, everything flows through this single unified system. And this works out great, because this means every single design decision, the outcome of every investigation is already available in this stack. This means that when global project teams, they can deliver on their products in a very independent manner. At the same time, everyone is feeding back their issues and fixes into the same system. Everyone is now an active participant in improving this software stack, and its benefits are being realized by everyone in real time as well. The final important goal for us was to identify our key use cases early on, and then develop a comprehensive solution for those. As an example, silicon FA is very important for us. The chips are really large, expensive, short in supply. We really want to go in and do a deep analysis for any time zero failures as well as customer returns. So we worked very closely with this team to design the most optimized methods so they can do their work very effectively, like 2 years later. Similarly, we wanted to reduce the effort for pattern creation within our teams as well. For a chip of the size of Blackwell, it's a massive amount of effort to create all of these complex pattern sets. And imagine having to redo them for multiple packages or power configurations and things. So again, from a very early architecture phase, we went in and implemented the hooks. So later, this work is done much, much rarely. And then we use the time we save to create more comprehensive quality patterns, because quality wins every time. So leading this project over the last 4 years was a great learning experience. I wanted to share the most important ones. They might be of benefit to some teams that are at a similar decision point today. First, the end impact of such projects is really high. If you have a workflow that's 5 to 7 years old, and it's a limiter in your day-to-day work, bug rates piling up, not able to do new developments on it, you should look at redesigning it using the first principles. It is tempting to do incremental fixes, survive another project, but the technical debt keeps adding up, and it's a much bigger problem to solve in the future. Second, high-impact work cannot be done alone. For this project, we worked very closely with various teams at NVIDIA: clocks, timing, physical design, place and route, test chip, operations, and many, many others. They all understood the value proposition for this change. They brought their expertise into this effort, and they were a huge factor in the overall success. Third, build on top of the most suitable EDS solution for your specific scenarios. Don't see it as outsourcing your test strategy to EDA, but consider it as enabling your engineers with the best that's available in the industry today. And then direct their talents to solve your most important challenging problems. All right, a lot of hard work was done over 3 years of Blackwell development. Let me share some of the context to highlight the challenges of this bring up. This was a brand new test architecture deployed on the most complex chip we have ever done. This is a CoWoS-based product, so the first bring-up was at wafer level with very limited set of debug tools. All the workflows have been rewritten. Any single thing going wrong, it can lead to days of open-ended debugs. So 3 years of hard work, 3 months of intense anticipation until the chip comes back from the fab, and the results were simply amazing. Some of the tests, when we ran them the first time, the shmoo turned out green. It actually happened. In 24 hours, we announced that the new architecture was working well. The maths PCIe-based solution came up soon after. Eventually, we have enabled production at 12 Gbps throughput. For comparison, this is same throughput as 400 scan-in and 400 scan-out pins. We use this massive bandwidth to double down on quality for our Blackwell product. The total scan payload data on this product is 80 gigabytes, 50 GB of which is what we call advanced coverages, things like cell aware, small delay, and some of our internal developments as well. Test time is not a strict limiter either with maths. So we run the same test at multiple voltages, frequencies, and temperatures, and we try to filter out the very marginal defects at the wafer level itself. So to summarize, the redesign of NVIDIA scan solution has enabled us to deliver the best quality available in the market today. And it has set up a great platform for the next several years of innovation. We look very much forward to the next phase of this journey. We will also be presenting a technical paper on this work later this week. It's on Thursday, 11:30 a.m., and I invite all of you to that presentation. The final thought that I wanted to share today is the idea of a quality architecture. In our industry, we have design architecture, verification architecture, test architecture. I think there is room for something new, what we might call a quality architecture. This would be a systematic approach to ensuring silicon quality, spanning the entire life cycle of the products. It would start with what we do well, our ATE capabilities, test coverage, stress test, yield improvements, et cetera. But it would extend further into the complete silicon life cycle from individual chips all the way to the entire data centers. In each of these environments, system-level tests, board-level tests, system deployments, new capabilities will need to be created or made more accessible and efficient. And it also acts as an enabler for silicon lifecycle management, or SLM in short. And who knows, perhaps the two things become the same thing down the road. While the specific details would be too many and will be figured out over time, I wanted to make 3 points that I feel are very important for this vision. First, we should be able to release most complex test patterns to every part wherever it is, whether at system level, board assembly, or out in the field. Modern chips are very complex, and we will certainly learn new things over the 3 to 5 year lifespan of a product. It would be a huge step forward to deploy these learnings to the fleet on an ongoing basis. Second, we need to be able to bring back a lot of data from the field to the engineers working on test quality. Without real data on what's working well, or common symptoms from a large number of failing parts, the engineers are really working blind. Third, it will require the various players in the industry, large and small, to all work together in creating the various solutions for this stack. I hope that at ITC, many such discussions will get started, and we will all find new ways to move the industry forward. Thank you, everyone.